Section 2.3 and 2.4, limit laws and continuity. So the very last diagram we looked at in section 2.2, that was the one that looked like this. We had a graph and it sort of came up here, and then there was an open circle and it went like that. We had an open circle and then like that, and I think there was a dot down there as well. This diagram right here really gives us the sense of what we need to know about continuity. The idea is that at this spot right here, there's a break in the continuity of the graph. Okay, there's a gap there. And we've got a gap here as well. The third spot we looked at though was right here, and there's no break. It just sort of goes through that dot like a normal graph. And you may recall, or you may want to look back at section 2.2 to remember this, when we looked at this one, all the limits and the actual functional value there were all the same. They were all equal. But for this one and this one, they were different. And so this is what will lead us to an idea of continuity, not just graphically, but algebraically. What does it look like when we actually look at the functions? So our definition is this, definition of continuity. Your function is continuous if the limit as x approaches p of f of x is equal to f of p. And it seems very straightforward, but there's actually three important things that need to be verified. First of all, we need to have f of p defined, so it needs to actually exist. The second thing is we need to have the limit as x approaches p of f of x exist. Okay, so we need to have this side exist, and we need to have that side exist. And the third thing, it's not just that they exist, but they have to actually equal one another. And most functions are continuous almost everywhere. Most functions we'll deal with are going to be continuous in most places, and there'll be one or two spots maybe where they're not continuous. So the easiest way to get a feel for continuity is actually to look at the places where it fails, at places where you have discontinuities. A warning about this, though, is there are actual functions that are not continuous, that are, I should say, discontinuous everywhere. You can define a function that will have a discontinuity at every single spot that you can find. These are rather complicated functions, but they do exist. So there is actually a lot more to this concept than what we're going to get to in Calculus 1. And what I want you to do now is we're going to look at this exercise. I'll go ahead and do part 1 of the exercise, but then I want you to do the rest, and I want you to basically look at these functions and try to figure out where the function is discontinuous and also what part of the definition it fails. And it may help you to graph it, it may help you to just sort of look at the function and figure out where places where it's not going to be defined. But go ahead and let's do part A together, and then I'll have you pause the video. So we're trying to look for discontinuities for the function 1 over x. And just looking at that, I can tell that there's going to be an issue at x equals 0 because f of 0 equals 1 divided by 0 is not defined. So this means that f of 0 does not exist, which means that it fails part 1 of the definition that I put up above. You need to have the actual functional value exist at that spot where you're looking for the limit. Interestingly, if you graph this, the graph looks like this. On your graphing calculator, it may want to try to connect those two, but there shouldn't actually be anything there. There's actually a vertical asymptote in between those two. And what's interesting about this is as you approach 0 from the right-hand side, so the limit as x approaches 0 from the right, that's actually going up to infinity. That limit, that one-sided limit, does not exist because it's not actually going to a number. And the same thing with the one from the left. So in this case, the limit as x approaches 0 of f of x also does not exist, which means that it actually fails part 2 as well. Okay, and you only need to fail one of these parts in order to be discontinuous. This one happens to fail both. Go ahead and pause the video now, and try to answer B, C, D, and E. So try to figure out where the function is discontinuous and what part of that definition it's failing. Pause the video now, work on that. You can unpause it if you get stuck or when you finish. Okay, so for B here, once again I notice that I've got an issue with f of -3, because that would give me a 0 on the bottom. So looking for a spot where I get a 0 on the bottom is always going to be an issue. So if I plug in -3, I'll get 0 on the bottom. -3 plus 3 will give me a 0 there, and -3 minus 2 gives me a -5. -5 times 0, though, is just 0, and 0 over 0 makes no sense. So f of -3 does not exist, which means it fails part 1, just like the one above did. Interestingly, if you graph this, and maybe we should do that, if you graph this, this is x minus 2 times x plus 3 divided by x plus 3. And I'm going to zoom out to get a better look at this. When I zoom out, all I get is this straight line. And I was saying that we have a problem with continuity at x equals -3, but when you look at the graph here, it doesn't seem like there is any problem. It looks really just like there's a straight line. When you come over here and look at the table of values, you notice an issue. At -3, it's not giving you any number here. So what's going on here is we've actually got a hole in the graph, and the computer and the calculator doesn't understand that. So it tries to graph the whole thing right there, but in fact the graph looks like this. Here's -3, and there's -5. There's a hole, and the graph looks like that. The hole is very small though, so it doesn't show up on the graphing calculator. And what's interesting about this is that the limit as x approaches -3 of f of x. According to our graph, it looks like our y value is going to -5 from both sides. So the limit actually exists. So it satisfies part 2, fails part 1, so it's discontinuous. Now letter C, here we've got a split function, a piecewise function, and oftentimes the continuity issue you're going to run into here is at the place where the split is. So it splits at x equals 1, so I'm going to look at what happens there. And if I graph this, let's see, here's 1, and it says that f of x equals -2 if x is less than 1. And that graph looks like that. And it's equal to x squared if x is greater than 1, greater than or equal to 1. So I put a solid dot up here. This is at x equals 1, and it goes that way. So I can see on my graph I've got a break here. So the gap does in fact happen at x equals 1. And what am I going to do with this? I can figure this out by looking at, how about f of 1? What does that equal to? Well, f of 1, that means I just plug in 1 to whichever spot it's defined at. Here, for x is greater than or equal to 1, the equal to 1, it tells me I have to plug it into x squared. That just gives me 1. So part 1 of the definition is fine. F of 1 actually exists. It's equal to 1. But if I look for the limit as x approaches 1 from the left, when I look at that, I'm looking for x values slightly smaller than 1, so that's x values over here. And the y value that I'm always getting is -2. So this limit is giving me -2. When I'm following along with x values less than 1, it looks like my y value that I'm going to hit is -2. Now the limit as x approaches 1 from the right of f of x, from the right I've got numbers slightly bigger than 1, so I'm looking at x squared. I'm looking at this part of the graph. when I'm following this part of the graph, it looks like my x values are getting closer and closer to 1. Sorry, as my x values get closer and closer to 1, my y values are also getting closer and closer to 1. So that's equal to 1, and because these are not the same, my limit as x approaches 1 of f of x does not exist. Now for part D, we basically have the same graph that we had in part B. So here's -3, there's -5. We've got an open circle there, and the graph goes through here. But what I'm adding is, this is only for x not equal to -3. When x is equal to -3, I'm defining, let's call that -1. I'm actually putting a dot right in that spot. So I've got an open circle here, and there's the dot. So in this case, what is f of -3? Again, I'm looking for the potential issue at the place where we have a split. F of -3 is what is the functional value when x is equal to -3, and that's telling me the way the function is defined, I look at this line and I get -1. Now if I want the limit as x approaches -3 of f of x, these are all values that are not equal to -3 but are close by. And as you can see from this graph, and as we saw above, that limit in fact is equal to -5. That's the y value I'm expecting down here, but it never actually hits it because there's an open circle. So here part 1 is okay because that's defined. Part 2 is okay because the limit is defined, but f of -3 is not equal to the limit as x approaches -3 of f of x, because this one is -1 and this one is -5. So it fails part 3 of the definition of continuity. And the last thing I want to mention is, for this last example here, part D, what could I change about this function right here? If I wanted to say, redefine this somehow or change a number to make this thing continuous, how would I do it? And what I'm looking for here is this dot right here. Basically, suppose instead of putting that dot up here at the y value of -1, suppose I put it right there at the y value of -5, and I filled in that hole. That would then make the whole thing continuous. So the answer I was looking for here, and there are multiple answers, there's other ways to change this. Let's just change that -1 to a -5. Then it will satisfy part 3 of the definition of continuity, because we would have a -5 here, which would then match up.